Good afternoon, colleagues. A warm word of welcome from the Govan and Mbeki Mass Development Center to this first Geogebra for Innovative Practice webinar that we have as a pilot this afternoon. So we would really like to thank you for the time and the effort to be part of this. Quite an exciting event. It is something new we will try today using GeoGebra specifically for problem solving, creative problem solving, to demonstrate that, to also try to promote STEAM education in general. So we've got quite an interesting program, I think exciting, so hopefully you will enjoy this. And the purpose of today's event is to really demonstrate the potential and the power of Geogebra Applet technology as a valuable vehicle to teach the CAPS curriculum, because that is the goal in the end, to be able to also support our learners in the curriculum delivery through methodologies like this with the technology, and particularly also to promote STEAM education and creative problem solving amongst our teachers, and hopefully to also empower them to be more, powerful and to deliver the curriculum, and to also to promote problem solving in a much more powerful way going forward. The method for today will be quite interesting. There will be presentations or demonstrations of GeoGebra Applets online, but there will also be the opportunity for all participants, and I really invite everybody. We shared with you in the communication earlier to try and prepare your phone, to set it up, to be able to capitalize on accessing applets on your phone, the applet that will be demonstrated using a QR code specifically today, but in general, we'll be also able to share these via hyperlinks, just straightforward links and QR codes. But for that today, your participation will really depend on accessing these applets using a QR code that we will display on the screen as we go along, and we'll say a little bit more about that as well. Now, as you can see on the screen, we have a program consisting of 6 sessions, not too long, 15 to 20 minutes. I'm Werner Olivier. I'm the director of the Govan and Mbeki Mass Development Center, for those who don't know. And I'm going to present this with a number of my colleagues that I will also introduce very soon. But you will also notice that we even have a guest today. We are very privileged and happy to have Fatima Jakut, who is also the founder member of the Saki Kamfa Foundation. We have a relationship with them. So in the second session, if you can see on the screen, she will also give, I think, a very exciting and valuable presentation linked to pedagogies in the 21st century. I will take care of the first session today, and so will some of my colleagues. I will also take care of the third session, which will more deal mostly with problem solving, creative problem solving, mathematical problems, and hopefully will be of great interest to teachers, particularly as we will try to link it with the CAPS curriculum as we go along. Some of my colleagues who will also present, Patrick Redindanswa, he will be taking care of the first session, Arnold Gwaze, and then Peter Weiswanger, colleague in charge of our science development program, will also demonstrate how GeoGebra Applets can be utilized for science demonstrations and teaching and learning right at the end of this webinar session. It is quite an interesting new journey for us, and we will try to introduce a new pedagogy today, which I don't think has happened before, unless somebody can remind me, in the context of utilizing technology effectively and creatively. We will try to utilize online Zoom session demonstration of a GeoGebra Applet, for example, but parallel to that, we will try to also get the participants to access and manipulate synchronously at the same time, these applets using a secondary device, a phone on your side. And this is all about trying to set up, interaction over distance for experiential learning of mathematics, science, STEM, and particularly also to promote STEM education. Finally, I just would like to introduce, also Karin Stein, our academic manager in the center, who will be assisting with looking at the chat and responding to some of the chats, as well as Natalie and Placid, our technical support person, who's also just taking care of some of the technical parts of the webinar as we have it today. Without further ado, we should just proceed with the first session, demonstration of a very interesting concept with various applications that has a direct link with the CAPS curriculum, where I would like to talk about the concept of a Voronoi and Delaney graph. So these are two complementary or dual concepts which has a very basic mathematical structure and very much something that can be widely applied in science, in mathematics, and something that also occurs quite broadly and widely in nature. So the idea is just to introduce you to these concepts. By the way, in some curricula across the world, this is part and parcel of the school curriculum, but not in South Africa. So this must be maybe very interesting as a concept or an application to show links between mathematics, not only engineering and other areas of science, but also between mathematics and art. Let me just start off by introducing this concept. So these are the persons that I'm referring to. George Voronoi lived in the 19th century, and his student, Delaney. So the Voronoi graph was first investigated centuries ago in a context of finding areas on a plane which are closest, points in the area are closest to a particular point that we start out with. So the idea is, just by definition, to start with a set of points, and for the purpose of the CAPS curriculum in mathematics, one can just view these up as points on the Cartesian plane. So let's say we start with a few points on the plane, and we're interested to see which regions in the plane are such that all points in a particular region, we refer to these regions as a cell, is closest to a particular point from the set that you start out with. And these points are referred to as C points or sites. Then there is a very, very simple geometric construction that is part and parcel of the CAPS curriculum that will really sponsor the generation of such regions in the plane. And as you can see that for any set of points, if you find these regions, you really tessellate or tile the plane. You have these regions which are non-overlapping that result as a consequence. A similar definition or similar approach can be utilized in 3D, but for the purpose of today's talk, I would just use the 2D approach in this context. So here we go. This is then a set of points, first of all, and we have the connection between points are such that it represents a perpendicular bisector. So any 2 points, if you look at the perpendicular bisector, then you find the graph as indicated. And I'll actually just demonstrate this definition again. Maybe I should just go back one slide. So technically you connect any point and you find a perpendicular bisector for that point. And this really gives you the boundaries of these regions, which are then referred to as the Voronoi graph of such a set of points. And the Delaney on the other hand is just the connection of these points using triangles, but not any point is connected to any other point. It is connected in a way such that if you take any 3 points and you draw a circumcircle for the triangle of those 3 points, there is no other point inside. So that defines the so-called Delaney graph. It's a triangulation of all the points on the plane, the points which you have, such that if you draw a circle, around 3 of them, circumcircle, there's no other point inside. So it's a very special triangulation with high-level applications in not only in mathematics, but in engineering and many areas of science. So the interesting thing is that the Voronoi and Delaney graphs are dual concepts of each other. In other words, they complement each other. Voronoi graph is to find a region where all points in a region is the closest possible. Straight line Euclidean distance, still in the CAPS curriculum, is the closest possible to a particular point. So these regions, but if you look at the Looney triangulation, that again gives you an idea of where the positioning or a point is, which will be the furthest away relative to 3 points. So the center of this circle, the second circle, will be the point that is furthest away from 3 points. And in fact, it will be the point that's furthest away from any other point in the set. So with these ideas, let's just have a look at some of the amazing applications and natural occurrences of these graphs in nature and where it can be applied in science as well. Now, the earliest possible reference to Voronoi patterns in space is by René Descartes, very famous mathematician, which really had a graph of the decomposition of space, will be a Voronoi graph. So there's the first reference. And then I'm just going to go through these slides because we want to go to the GeoGebra experience as well as the applications. In nature, we see many patterns, whether it's the skin of animals or whether it's the wings of insects and so on, that these Voronoi patterns, naturally occur because from a growth point of a cell, that gives you the region then which is optimal in terms of the closest distance with some properties to the center point. So these are all examples of Voronoi diagrams, even in 3D. And we do not have time to go into detail with all the examples, very interesting. So we'll share, and that's another thing. We'll share our presentations and also the applets, the GeoGebra applets that we will demonstrate with everybody after today's webinar session. Even a mud plane, if a mud plane dries up, it's a Voronoi pattern that results in relation to the definition. And here are some other examples of Voronoi patterns, even in our own body, the cells and the tissue and the growth. And together with that, there is also the connection with design, architecture, as you can see, where Voronoi patterns are sometimes used to do optimal design. And I've listed here quite a number of applications in science across various fields that you can have a look at. If we share this, then we also have the link with the arts. Voronoi art is quite a category, specialist category in art. And here we see an example of a Looney graph on a spiral with colors and some other examples that I'm just quickly going to mention, by ways of example. Now, this example here we, for example, have the London Underground train station map. It's a Voronoi map. Now, what does that mean? It means that these regions are all such that any point in a particular region is the closest to a particular substation. So it's important to know if you have your network of points, in this case, across a surface area, urban area, where, the closest possible, entry point is of a certain type, whether it's a police station or a hospital or whatever. So it's used a lot in the context of urban planning. And we will look at a similar example using the GeoGebra Applet as well. And this example on the right-hand side on the screen is just 2,980 airports in the world. So if you fly, and this is exactly the application that I would like to demonstrate with GeoGebra with you. Then if something goes wrong, you want to land as soon as possible. So wherever you are in that particular region, the closest airport is then the C point, or the point that generated the Voronoi graph in this way. So with this in mind, I think we go to the exciting part for today, where I would like you to join me to just get a feel of how this Voronoi graph concept and the dual Looney graph works, and particularly how we can link this to the CAPS curriculum in demonstrations, and also how we can link it to real-world applications. So I would like to just confirm, we shared this earlier last week as well, that if you have a phone and you have a QR scanner, then you can be able to access the applet that I will flash on the screen next, that will also allow you to interactively, work with me to actually demonstrate aspects of Voronoi diagrams and some applications of that. So hopefully all of you are in a position to scan a QR code which will give access to a Geogebra applet. This is the activity with Geogebra. Very excitingly, I put together a series of these applets for various purposes, just to demonstrate the potential and the power of Geogebra to be utilized in this case in this way to demonstrate, either problem solving concepts or even just to use as a demonstration of an interesting concept and application linked to mathematics like I have here. The applet. So if you go with your phone, scan the QR code, you should see something like this. Clearly, you have to turn your phone sideways to be in landscape format. And then at the bottom right-hand side of your phone, I know the phone screen is very small, so just be very careful. You have to touch this button over here, which makes the applet then in demonstration or slideshow mode. And this is the way that we will interactively then discuss and demonstrate what is meant by a Voronoi diagram. Now, let me just immediately say there are a couple of things that we can do with Geogebra applets, even with phones over distance in the way that we have it set up now, that are very, very simple for you to interact with. First of all these blocks, the colored blocks, if you touch them, you will see that it actually just gives you a pop-up picture or a set of information. In this case, what is the Voronoi diagram? If you want to have a look at the definition, explain, you just switch it on and off by touching that block. And same with the learning. We have already looked at that, but that is just for on and off. And in all other cases, you can do the same. But the other important thing, which is very important for this activity, you must be able to slide the slider with your finger. Drag your finger across from left to right. This enables you, as you can see on the screen, to define the number of points that you will want to investigate on the plane. Let's see this as the Cartesian plane, and we have points. So let's agree together to only have 5 points on the Cartesian plane. So hopefully, while I'm talking here and demonstrating, you can also do exactly the same by touching the point and dragging it. That's the other thing that you can do. You can actually drag this point and position it wherever you want to. So please, if you can just practice with me and see that you can manipulate this particular set of points on the plane. Another button, this is also a button that you can just click or touch, in your case, not click, to reset the point. So you can reset the position of the point and you can drag it again to wherever you want to. Now, let's demonstrate again. What is a Voronoi diagram? It has to do with the perpendicular bisector of the segment between any two of these points. And if you select up here this button, select Voronoi diagram, you can see that you have immediately generated the Voronoi diagram for these 5 points. And clearly where you can manipulate the point, so you can see how the positioning of the point then actually changes the tessellation of the plane. Remember, tessellation means you're breaking up this plane into the regions. These are the regions, or the Voronoi cells, as they are called. And what is that? It means that any point, for example, in this region, this Voronoi cell here, any point will be closer to this point than any other point. So it's the nearest neighborhood, demarcation of the plane, which has huge, valuable applications in science and in many areas of nature. So let's see again, how did that happen? If we selected the linear triangulation on top of that, in other words, the triangulation, can you see that any 2 points that are connected, this is the perpendicular bisector of that segment, and so on. And not all the points are connected and triangles, only those where, for example, if you have a circle around these 3 points over here, you can see that that circle does not contain any other point. And only those triangles are allowed to be a set called the Delaney triangulation, which is also very important, and applications in computer graphics makes you use a lot of that, and also in computational geometry. So if you increase your number of points, you see there are more and more points that you can then also drag individually. So just get a sense of how the region demarcation in the Voronoi regions changes, as you have the number of points. Clearly, we can't have less than 3 points. So that's a triangle. You can even start with that if you want to demonstrate and investigate the region division of a plane. If you have 3 points where perpendicular bisectors are used as a basis to construct it. It's very clear intuitively if you think of it. If you only have 2 points, then clearly you'll have to divide the plane into 2 halves, really. So you only start with 3 points as the starting point for meaningful, Voronoi diagram, as well as the dual concept of a Delaney triangulation in this context. Okay, so how do we apply that? And I would like to end off my presentation, the first one, by just looking at some applications. So I would like you to touch this particular button called Examples of Airports in South Africa. I would like to find the regions across the country where if an airline pilot gets in trouble, he can immediately see where the closest airport is. So in this case, I will count the number of airports denoted here by the icons of the planes across our country. I see there's 11, so I can say I need 11 points. And by the way, you can switch off your Voronoi and the Delaney triangulation just to make it easier for you to start this application. So switch it off and set your N value for the slider to 11, and then position, and hopefully you can do it with me. I would really like to know if this was possible on your side, if you have the phone, and if you have access to the Geogebra Applet as I demonstrated at the moment. So I'm putting the points exactly across where the airports are, and in this case, I think I've got an extra point here. I will then be ready to select the Voronoi diagram, and you can see it immediately gives me the regional demarcation where if you fly and you find yourself anywhere in this region, for example, then Bloemfontein will be the closest airport, and so on. And there are many other applications in terms of, urban design, etc., and also where is the closest hospital, police station, and so on that can be determined using the concept of a Voronoi diagram. Let me demonstrate the one practical application of the Delaney triangulation by just looking at the second example that I put here in green. So if you touch this particular button, you'll see that I have here some restaurants in Bloemfontein from Google Map. I again switch off, first of all, my Delaney and my Voronoi diagram. And in this case, I think there are 10 or 12, I'm not sure. But positioning the points then, where I've just chosen the Wimpy as a restaurant. I don't know how many of you favor the Wimpy restaurants, but nevertheless. And the idea here is to answer the following question or the problem, to solve the problem. If you want to open another Wimpy restaurant, where would be the best place to place it or to position it? Maybe I've got less than I thought here. So let's say we cover all the Wimpys in this case. There are 10 of them, all right? Clearly, if I want to open another Wimpy restaurant, it must be as far as possible away from existing Wimpys as they are represented on the map. So in this case, you can have a look at the Voronoi diagram. So, for example, if you stay in this particular neighborhood, and you would like to go to the nearest Wimpy, you'll go to this one. So it gives you the nearest. Due to that, if you look at the Delaney triangulation, interestingly enough, and I switch it off, these particular vertices of the Voronoi diagram are exactly the center points of those circles, the circles that circumscribe the three closest, set of seed points that you have for this particular case. So for example, if you look at the circle around these three nodes or three Wimpy restaurants, the center of that circle will be particularly that node, which is the node given as a vertex for this Voronoi diagram. So that position is the optimal position, furthest away from any other point in the set of points that you use to seed your Voronoi diagram. So there is many interesting applications of Voronoi diagrams far and wide, and also it is at various levels. Very simple application, as you can see from looking at this situation or this application, to the most complex, applications in science and technology. So hopefully you were able to interact with this applet. So this is just an example of a GeoGebra applet where you can demonstrate and experiment and discover for learning purposes, applications, but concepts even linked to mathematics, and in particular even to the CAPS curriculum. So I will stop right there. I'll just reset here and just stop my share, or in fact, I'll just do a new share again to go to the presentation that I had before, and particularly the program. Now, okay, so in that case, I will then go immediately to the second GeoGebra applet that I would like to demonstrate. Now, this is a problem-solving applet where the idea is to demonstrate the creative solutions to level 4, taxonomy level 4 problem, and also to demonstrate some creative solutions using a GeoGebra applet in this context. But before I do so, I would really like to make sure that everybody, or as many as possible of our participants, can meaningfully access the applets and work with me. So if I can just for a moment look at the new share. Right, so hopefully everybody sees this particular share at the moment. And again, allow me to just share again the method and the steps that you have to follow to access the applet, as I will demonstrate or show the QR code in the next slide. So here is the one that I would like to demonstrate. So instead of having session 2, we'll now have session 3, and my colleagues will follow with session 4, 5, and 6. Colleagues, this is a very interesting problem, and all mathematics teachers should be quite interested and excited about the solution of this problem, which is directly also linked to the CAPS curriculum, and we'll point that out, but also to be able to interactively and dynamically demonstrate the solution in its various facets, I think is quite an interesting prospect, which I believe is possible using the methodology that I'm trying to demonstrate right now. So while I'm speaking about this problem, which is all about inscribing two squares in a semicircle, and the question around that, what will be the sum of the areas of those two inscribed squares? That is the question. While I'm talking, please take your phone and scan this QR code, and then I will work with you through the solution and the demonstration of the affordances of the GeoGebra applet to be able to really, I think, interest learners, and also to demonstrate creative solutions where basic results in the CAPS curriculum are utilized. Nothing more than that. So hopefully most of you were able to access the applet using the QR code. So I'm going to go there myself, and then I'll just share again, new share, to be able to share with you in this regard. So here we go. This is the applet. And by the way, colleagues, what I'm doing now and what you're doing, you're going directly online to the GeoGebra global platform where all these applets are hosted. So the wonderful thing about this method or this strategy is that you do not need GeoGebra software at all on your device. Whether it's a phone or a laptop or a PC, you don't need to install any software. You can directly utilize the GeoGebra software as an applet online and very, very low data. So if you're worried about data, don't be. The data usage for GeoGebra applets is extremely low. Right, so if you're with me, remember the first step is you have to turn your phone sideways, and then you have to select or touch the button on the bottom right-hand corner for full screen mode. So you have to be on full screen mode to be able to interactively work with me in a synchronous way to try to solve this problem. So in the context of problem solving, clearly the first step as per Polya's plan, for those who know George Polya, the father of problem solving, is the first step is to understand the problem. And then, of course, to design a strategy and then implement it and then reflect. And that is the way we're going to do this using this particular applet. And there's actually too much to demonstrate and talk about for the time given. So I'll just try to be very sparse. But again, you see we have sliders here and we have buttons that we can, touch or select. That's important for this particular application. It's important to understand the problem first. So you can see there we have a semicircle and we have a square, two squares adjacent, inscribed. Inscribed means that the vertices on the outside must not be outside the semicircle. It must be at most on, it must be on the semicircle. Inside, it can be inside, but no vertex of the squares must be outside. Hey, that's inscribed. So clearly, the first question could be, how can we do this? How can we actually create or construct such a set of squares inside a semicircle? Obviously, we can just put a point there, and then that becomes the height or the y value for this point. Let's say it's the point A0, becomes the side length of the square. That's easy. But what about the second one? That's definitely not so easy. It's quite complex. It's doable. And we can actually solve that question of how to construct this point B once you have selected point A, such that you have two squares in this particular way. One way of doing it is to have an analytical approach where you actually force distances to be the same, especially for the second one, once you've chosen the first point. And that you see at step number -1. I put it up in the step -1. So you can actually go through this. We don't have time now. And that's a nice analytical way using exactly the Euclidean distance. That's the only thing, which is also part of the CAPS curriculum, and the function and roots to be able to find that point, which then gives you the second square. But that's not the point of this question. The point of this question is, if you have such an inscribed set of squares, what will be the sum of the two areas? And in particular, if the radius is equal to 10. So this question was, stated for the case where the radius is 10. Now, the first question that I would ask if I'm a maths teacher or even if you are interested in mathematical problem solving, if I say that the sum of the areas, who says the sum of the areas will be the same for all positions? Because in my view, and that you can check by just animating. If you animate, you can see these are the possibilities. These are all two squares inscribed in a semicircle. So does this area stay the same if I sum the two areas for the two squares? It's implicit in the question. Otherwise, the answer will not make sense. So we can assume that the answer will be the same. And that's quite a surprising result in its own. And to touch this particular orange button, colleagues, you will be able to reset. So you can always animate and reset. And this is a very powerful affordance of GeoGebra Applets, to be able to dynamically demonstrate the various cases and then try to answer questions or solve problems in relation to that. Okay? So to understand the problem first, I don't think that's a problem. Everybody understands the problem and more or less what it entails. And that is infinitely many cases of inscribing 2 squares for a particular radius. In this case, the radius is 10, right? Good. Now to solve this, and this is where we have used in this case and in other cases that we will follow as well, a slider to just show the steps of the solution. And every step can be discussed with all its questions and interactive discussions. So the first step is to, of course, identify the variables that will assist us possibly to find the sum of the areas, area 1 plus area 2. And if we assign a variable s to the side length of the one square and t to the square side length of the second square, then clearly we're just looking at s squared plus t squared. What is the value of s squared plus t squared? And all that we know in this case is that the radius is 10 for this particular situation. Note also, it's part of the CAPS curriculum, if you have a semicircle or a circle for that matter, and you shift it 10 units to the right, this is the defining equation, which will also allow you to get a sense of, how to construct these particular squares if you're in that space. What is the next step? We have to see something creative here, and this is where the creative part of the problem solving will come in. We need to notice the symmetry and the fact that the properties of the square is the only thing really that I can work with. So looking at the diagonals AC and BC, immediately we have angles 45 degrees, and we have the length of these diagonals in relation to the side lengths S and T. So that's a very good starting point. And if we now animate as well, we can see, it doesn't matter which squares are being inscribed, those angles remain 45 degrees, as we expected. But that gives us a very interesting angle to try to solve this particular problem. And that is the fact that the angle ACB is 90 degrees. So AC is perpendicular to BC. And whenever we see perpendicular angles and a triangle, if we also look at AB as a chord for the semicircle, then Pythagoras becomes, something on the horizon to try and to think about, and it's exactly the same in this case. So, for example, if we can find the distance AB by Pythagoras theorem, we can see immediately that if we have the square of the one side plus the square of the other side, we get the square of the hypotenuse. And this turns out to be exactly twice the answer that I'm looking for. It doesn't give me the answer, it just gives me twice the answer that I'm looking for. So if I can get another way to generate, for example, this distance AB, which is directly linked to the answer, then I may be able to solve this. And this is where another creative step comes in. And this step is directly linked to the CAPS curriculum, in particular the focus area of circle geometry in grade 11, I think. So if, for example, I reflect, making use of symmetry of the circle, and I reflect these squares about the x-axis to make it a full circle, clearly this angle remains 45 degrees because we still have a square. And suddenly AX and B is 45, but that is the angle subtended by the chord AB on the circumference, which means that the angle subtended at the center AOB must be 90 degrees. And that is probably the key to the geometric solution. There are other solutions as well to the geometric solution of this problem. Why? Because we know that AOB, these are radii. We know the distance, in this case, both for S and T will be equal to R, if that is linked to that. And that gives us then finally the answer in this case. And the answer in this case will be just, R squared in this case, because twice R squared gives me AB squared in a second way of linking with Pythagoras the distance AB, AO, and OB. But we could have shortcutted that, and I've built in this particular button to really show the case when these squares are equal. One of those cases where we have the inscribed squares, where the side lengths are equal, if S is equal to T, it will be exactly this situation, which I've modeled here. Okay, and if you have this as a special case of the inscription range that one has in this case to try to solve the problem, I think this problem will become very much easier, and you could have seen the answer immediately in terms of this. So, question, if the answer is 100 for the sum of the squares of the, or any two squares in this way, in a semicircle with radius 10, what would be the case if the radius is 9 or 8? And surprisingly, this is the result that is always true. So you can always generalize and reflect as the last step of Poly's problem solving and discover, but well, this is just a special case of a more general situation where the sum of two inscribed squares in a semicircle will always be the square of the radius of the semicircle. So I think that really just hopefully would be quite interesting, and it would give you an idea of how to facilitate step by step, and you control this all the time, the various aspects of the solution of a problem for discovery purposes, for demonstration purposes, or otherwise. So I think I'll just stop right there, and hopefully most of you were able to at least manipulate and work with me and to see how you can utilize Applet over distance or otherwise to facilitate mathematical problem solving. So colleagues, we will demonstrate two more of these mathematical problems using GeoGebra Applets, and please, as with the previous two, try to, as quickly as possible, access it using the QR code so that you can interactively then also work with the presenter. So the next presenter, it gives me great pleasure to introduce Patrick Motredzanva from our center, who will facilitate a similar problem, but I think this one is probably linked to grade 9 or 10, somewhere there, where the one I presented, of course, directly linked, I think, to grades maybe 11 and 12. So Patrick, if you're ready, I'll just hand over to you then. Hey.
Thank you, Prof.
You can start your sharing.
Allow me to share.
Hey, yeah.
Yes, I'm going to give you time to scan my QR code to see whether it takes you to my applet. So I'm going to give you some time just to do that. Whilst you are doing that, I would just like to be explaining that this problem is a grade 9 problem. Now it covers 3 topics, mainly Euclidean geometry, properties of squares and rectangles. It also covers measurement, area of a rectangle and a square. It also covers algebra, simplification of algebraic expressions, and solving linear equations. Basically, to be able to answer this question, the grade 9 learners just need to have done those 3 topics. So I'm going to do a new share. I don't know whether you can see now my applet now in GeoGebra.
Yes, we can see it.
So on the bottom right hand corner, there is this small square. So I would like you with your phones on landscape mode to click on this square. Now clicking on that square, it will take you to this presentation mode. Now, before I move my slide, I'm going to explain the type of problem which we have. I'm going to explain because this problem is meant for grade 9 learners. It's not meant for you. But now using my applet, I'm going to demonstrate how easy it is to do distance learning using the GeoGebra Applets. Now, this type of problem is a level 4 problem. It's problem solving. It's taxonomy level, it's level 4. Now, for problem solving now, first you need to understand the problem. So I'm going to read the problem. A square is divided into 5 rectangular areas of equal area. The width of a blue rectangle is 4 units. Now the question is, what is the area of the square? Normally for our grade 9s, they know that to find the area of a square, you simply need to know just a side. You multiply one side by the other, then you've got the area of a square. But looking at my diagram now, using the formula is not going to work because now we don't even know the length of even one side. So I need now to understand the problem better. So I need to reread the problem to understand. I'm going to highlight some key terms which will help the grade 9 learners to solve this type of problem. So the key terms in my question are, it's a square. They know the properties of a square. Now in my question again, the square is divided into 5 rectangular areas. So if I look at my diagram, I can see 5 colored rectangular areas which covers my square. Now the key point again on my question is that these rectangles which are in the square, they are all of equal area. They don't have the same dimensions. Now with this type of problem, now for a grade 9, the problem is, where do you start? So I must be asking my learners some questions which will guide them towards the solution of the question. Now, since I've got 5 rectangles inside my square, my first question which I can ask them, which rectangle am I going to focus on so that I can be able to answer this question? Now, if I look in my question now, they say I'm given just little information that the width of a blue rectangle is 4 units. So I must start where the information is known. Now I must focus on the key rectangle, which is the blue rectangle. But now on the key rectangle, which is the blue one, the only side which I'm given is the width of this rectangle. And the information which is given is that the width is only 4 units. Again, even if the learners know the formula for calculating the area of a rectangle, they are going to have challenges because now the length is unknown. So now, if the length is unknown, I'm going to assign a variable to this length which is unknown. So you can use any variable. In this case, I can use a variable x for the length of the blue rectangle. I can use a different variable also for the length of the yellow triangle. Suppose now for the blue triangle, I'm going to use x as my variable. Now, if I read the question, that I'm going to see that the question says the 5 rectangular areas are equal in area. How do I find the area of the blue triangle? Now I know the formula they know from their studies from previous grades, that to find the area of a rectangle, you simply need to multiply the width by whatever is the length. In this case, the length is unknown, which I've assigned the variable x. So multiplying 4 by the unknown variable, then I will be able to find the area of 4x. Now, before I move my slide, I'm going to say now, knowing the area of the blue triangle, I'm told that all the 5 rectangles are the same. So whatever area I'm going to find for the blue triangle using the variable, then I'm going to assign all the 5 triangles to have that same area. Why? Because the question says the rectangles are equal in area. So allow me to now move my slider for the first step. Now, if I move my slider now, it shows that now my blue triangle, the length was not given, but I've just assigned a variable to this length. In this case, I just chose x. Now, my grade 9 learners, I can ask them now, what is the area of a rectangle with side 4 and the length x? Then they can easily say that the area is going to be length times width, which gives me 4x. Then since I'm told that all the rectangles are equal in area, whatever the area I get on the blue is going to be the area for the rest of the 5 rectangles. Now I can even ask now to say, what is the area of the yellow triangle? Even before I move my slider, then they are going to say, all my rectangles have got the same area. Now, having now assigned my variables now, then we can actually make use of the pictures to show that now the note to the learners to say, see now, interpreting my questions, all these rectangles which are different in color, they are all equal in area. Now, after that, now I need to isolate one of the rectangles to see what happens now. So I'm going to move my slider. Now I've moved my slider a bit now. I'm going to try to animate and isolate a portion of the square. So if I click on the rectangle on this animation button, I can see a motion which is, now I've got a smaller rectangle. Now I can reset, animate again. By playing around with the animation, I want my learners to see what is the length of this new rectangle. What is the width of this new rectangle? So I can play around with the animation. Whilst I'm playing around with the animation, learners will be able to see that the length of the yellow triangle, the length of the yellow rectangle is actually y from where the animation is starting. Now I can also ask them, what is the width of this smaller rectangle? Then I can always reset, start again, so that they focus on the side, which is now the width of my rectangle. Then they are going to say the height is, the length of my rectangle is y. The width of my rectangle is x. Then I can guide my learners towards the solution by asking some questions to say, now, do you know the formula for calculating the area of a rectangle? Yes, they are going to say it's length times width, which means in this case, to find the area of this rectangle, there are 2 ways. By the formula, I'm going to multiply y and the side x. I'll get the area of the rectangle, the area of the rectangle. Or since I'm told that now the area of one of the rectangles 4x, I can add all these areas which are inside. In this case, it is 4x plus 4x plus 4x to give 12x, or simply 3 times 4x. From their studies of algebraic expressions, they should be able to say, now looking at the rectangles, the area of the total area of this rectangle is 12x. Now I'm going to move my slider to show the solution. Now solution 1. Now I said now there are 2 ways of calculating the area of the rectangle. One of them is just by adding the areas of the smaller rectangles which are inside to get 12x. And the other xy I will obtain by multiplying the length of the rectangle by the width of the rectangle to find xy. So from my animated rectangle now, simplifying values of x, I'll be able to find my value of y as 12. But now, mostly with grade 9 learners, they will think that now, since I know y, the area of the original big square is going to be 12 times 12, then they get 144, which is a mistake. So we need to go back to the diagram and the question and find that y is not actually the length of our square. Y is actually part of the length. How do I determine the length of the square? So they know the formula that the length of the square, if you square it, you are going to get the area. So since y is 12, you add 4 units, you are going to get that the length of the square is 16 units. Just now, knowing that now to find the area of the square, which is now easier for them, you simply square the 16 and you get the 256 square units. Now, I think for solution 1 now, after that, our learners, they need to go back to the question and interpret to see whether, is this answer correct? So I will leave the interpretation to you. I'm not going to interpret now my answer. So the last part, they need to check, look back, check and interpret and see really, is it the correct answer? So you can always interpret so that you see you did not make any mistake. The clue now in the interpretation is now that to look at this brown rectangle. On the brown rectangle now, we already said now our length of this brown rectangle is 16. Now, but we are also told that the area is 4x. Then I can calculate the value of x from there to say, now dividing the area by the side, I should be able to find what is the value of x. Then I can actually interpret and see. Now I'm going to reset my applet again. Then this is the possible solution. I'm going to move again to the other possible solution. Now the other possible solution is I'm going to look at a different rectangle now. Now I'm going to start the animation. I can play around with the animation again to see so that my learners can focus on what is the length of this rectangle. So by playing around, they will be able to see that the length of this rectangle is actually y plus 4. Now I play around again with the animation so that they can see that the width of this rectangle now is also x. Which means now, as before, I can ask them, how do we find the area of the rectangle? So they are going to say from the formula, it's just length times width, of which now in this case, the length is y for the yellow rectangle plus 4 units for the blue units, which means the length is going to be y plus 4. And for the width, it's simply x. So from the formula now of calculating the area, it will be y plus 2 in brackets, then you multiply by x, you find one area. There is also a second way of calculating the area of this rectangle by simply adding the individual rectangles which are inside. So there are 4 of them, 4 times 4x, it gives me 16x. So this 16x must be equal to whatever was the area of the very same rectangle by using the formula. So I'm going just to move my slider to reveal the solution. Now, for me to calculate the area of this one, I simply say that it is the 4 rectangles, which are 4, each of them is 4x in area. There are 4, then they give me an area of 16x. Then by formula again, the side of my rectangle is y plus x, which is the length, and the width, which is just x. Then they will be able to equate because the areas are the same. So from my animation now, after cancelling out the values of x, they will be able to find the value y plus 4 being equal to 6. So if I look at my diagram again, I see y plus 6 is actually what I was looking for, which is the length of the side of a rectangle. So normally our grade 9 learners, they go further now to calculate what is actually the value of y. Then they are going to transpose 4 to the other side and say the y is equal to 12 units. Then after rereading again the question, they are going to find that they are only asked to find the area of the big square. Then they will have to go back again and say that 12 plus 4 is 16 back to the previous solution. So we emphasize that once they found the side of the side of the square, they simply square it to find the area in square units. Now the challenge now which I can ask to my grade 9 learners is of these two solutions, which is solution 2 and the previous one, which was solution 1. Which one is the easier of the two? Then they can make a choice of whether it's solution 1 or it's solution 2. So I go back to my second solution, which is that one. So there are two ways of actually calculating this, the area of this square, solution 1 and solution 2. So, but these are not the only solutions which I can use to calculate the area of the square. Other learners can come out with a different solution. Now I can actually challenge them to say, are there any other ways of calculating the area of this square? Now, the possibilities now for that challenge is now, it's also possible by forming 3 equations with 3 unknowns. How do we form the equations now? So now the challenge now which I can leave to my learners is that now with these 3 equations and 3 unknowns, they should be able to calculate the area of the square. I leave that one as a challenge to see, is it possible? Thank you.
Thank you very much, Patrick. That was well done, and I think a very well thought out demonstration of the use of Geogebra Applet for problem solving with linkages to the curriculum at a certain level. So if I can just try to share again here to get to the program and introduce our next presenter. I hope everybody can see that fine. So without further ado, I would like to introduce Arnold Gwaze, one of our project leaders in mathematics, to present to us the next problem, which I think it's quite an interesting one, because some problems even have historic context, and we try to not only link problem solving with the CAPS curriculum, but also to refer to historic significance of some of these problems. And the one that Arnold will be presenting is in that category. And also, wherever possible, to share some practical real-life applications of problems that we want to demonstrate via the Geogebra Applets as well. So Arnold, over to you. You will talk to us about how to solve the very classical half-moon problem of Hippocrates.
Thank you. Thank you. Am I able to share? Hello, everyone. This is Arnold Gwaze, as Prophet said, broadcasting live from Geogebra. This afternoon, I'm going to talk about the half-moon area, which is also called the Loon of Hippocrates. As I speak right now, I encourage you to capture the QR code that I have on my right there. And what I'm going to talk about briefly is a question where during this time, the value of pi was not known. It was about 200 years before the value of pi was known. So the idea was to calculate the value of the area of the Loon. The Loon is actually, I'm sure we have seen the moon at some stage, the half moon at some stage when it's up there. And this one is also called the half moon or half Loon. So the idea was to try to find out the area of this part, this brown part, which is actually somehow a difference between this half circle or semicircle and also this semicircle. So the idea was, how do we square a curved area, that is using straight lines or straight linear dimensions in order to calculate a curved surface area? The question that I have here is supposed to be solved by learners that are around grade 10, and the taxonomy level is supposed to be level 4. And what we are going, the topics that are covered in this particular question include measurements, Euclidean geometry, and also the Theorem of Pythagoras, areas of segments, semicircles, triangles, and all that. So it captures quite a lot. All right. Yeah. We have the QR code, which I hope you already have. And then this is what I was talking about. This is the Loon, the brown one. And this is a semicircle. This is another semicircle. So the Loon is sort of like a protrusion between two circles that are intersecting. So the idea was, how do we calculate the area of this Loon? That is what Hippocrates did. He was born in 470 BC and died around 410 BC. So somewhere thereabouts. He wanted to calculate the area of the Loon, which is sort of like a curved area, but he had to use straight lines. And this is how we are going to find out how he used the straight lines. I told you about the topics that we are going to use, and there are also questions that we are going to toss here and there. Right now, I need to do a new share so that we go to where you should be right now. Right, as Patrick said, or Prof also said, you just have to scroll, and when you scroll, please scroll next to GeoGebra here. So you scroll down, and then this will take you to this small square down there, and then you click there, and this will take you to your Applets. Now, let's go to the question. The question says, the green triangle fits into the semicircle AFBCOA, AFBCOA. That is the larger semicircle. That is where the green triangle is. It's inside, centered at O as indicated. The midpoint D, the midpoint of the green circle here, this part, the midpoint D of the hypotenuse of the green triangle is the center of the semicircle that defines the brown Loon as shown. So as we know, before you do any calculations, you need to understand what is happening. You need to know what is being referred to. So this is the side on the triangle which forms the semicircle that we have here. And then we have the brown Loon here, and we have a segment ADBF here. And then the question is, what is the area of the Loon if AB is equal to 2 centimeters? AB, this one is 2 centimeters. And then if you want to see the quarter of a square, that is a quadrant, that red one, that is the quadrant. And this is supposed to draw your learner's attention when you are working with them. Now, there is a hint here which says we are going to consider the theorem of Pythagoras we are going to consider the area of formula of semicircles. Right. As I said earlier on, we cannot calculate the area of the semicircle because during this time, pi was not known. So there are other means which we are going to investigate. Now, before I go any further, there are some things that we need to establish. We need to establish that from O to A, this is the radius of the larger circle. And from O to B, this is also the radius of the larger circle. And then we have a right angle here, and we have a quadrant there. What does that mean as far as this triangle is concerned? It means that this triangle is a right triangle and is also an isosceles triangle. If this triangle is a right triangle and is isosceles, you are going to ask your learners, what is this angle? What is this angle? And they will tell you this one is 45, this one is 45. Now the relationship between this side, that is the diameter of the larger circle, and the diameter of the smaller circle, we need to determine that. Now let me just slide for the steps that we are talking about. Right. We are going to see that AO is equal to AB over root 2. How do we determine that? If we talk about the cosine of this angle, BOA, cosine of 45 is 1 over root 2. And that is AO over AB. AO over AB is equal to 1 over root 2. So here we have AO is equal to AB over root 2. I just transposed the AB from this left-hand side of the equal sign to the right-hand side. That is a property that is important in a square or in a triangle or in a right isosceles triangle. What does that mean now? It means that AC is equal to root 2 times AB. Where is AC? AC is this one. AC is equal to root 2 times AB. We were here talking about AO is being equal to AB over root 2, that is AO, but now we are referring to twice that. So we are multiplying AB over root 2 by 2, so that we rationalize and we end up with AC being equal to root 2 multiplied by AB. And then here we have what I said earlier on in isosceles right angle triangle. Now, the area of this is related to the square of the radius, and the area of the smaller semicircle is also related to the square of its radius. Now, if we square, that means if we square AC and we square root 2 of AB, then we have a relationship between the two areas. Let's go to the next step. Right. Here we are saying the area of the bigger semicircle is actually equal to twice the area of the smaller semicircle. Now, that being the case, there is something that we know. We know that also if we have a quadrant, its area is also related to the area of the related semicircle. The quadrant is actually half in area of the bigger semicircle. The bigger quadrant is half the area of the bigger semicircle. Now, we have two relationships. We have the area of the quadrant being half of the area of the semicircle. And we also said that if we multiply the area of the smaller semicircle, we get the area of the bigger semicircle, meaning that the area of the smaller semicircle is actually half of the area of the bigger semicircle. Now, that being the case, it simply means that the area of the quadrant is equal to the area of the semicircle. Let's move. The area of the quadrant, which is this one, is equal to the area of the smaller semicircle. Now we are getting closer to something. Right. Now the next thing that we want to do is we want to find the area of the Loon. The area of the Loon is actually the area of the smaller semicircle minus the area of the segment. But we agreed that the area of the smaller semicircle is actually equal to the area of the quadrant that we have here. And we realized that the area of the segment is actually common to the area of the smaller semicircle as well as the area of the quadrant. That being the case, if you follow what we have here, which I'm not going to explain, I'm going to explain it simply by saying that we want to take away the area of the quadrant so that we remain with the area of the Loon in the area of the smaller semicircle. But the area of the smaller semicircle is equal to the area of the quadrant. And this area and the segment is also common in the two. So in other words, in order for us to get the area of the Loon, we can look or focus on the area of the quadrant and simply subtract the area of the segment and remain with this area, the green area of the triangle, and that becomes equal to the area of the Loon. Now, we are told that we are given the dimensions of AB, and we are told that it's equal to 2 centimeters. What does that mean? It simply means that the area of the triangle is actually equal to 1. And how do we get 1? Let's go back. We have square root of 2 here. And by using the Pythagoras theorem, if we square this, we are going to get, sorry, we have 2 here. So if we square this, we are going to have 4. And we know that this is equal to this. So if we call any one of these two radii x, that means x squared plus x squared is equal to 2 squared. So 2x squared is equal to 4. That means x squared is equal to 2. And x becomes root 2. So we have root 2 here and root 2 here. Now that we have root 2 and root 2, the area becomes half multiplied by root 2 multiplied by root 2. And half multiplied by root 2 multiplied by root 2 will give us 1, which is what we have here. And I think there is something that is missing there, but let me just cross over to the historic note. This is what was done by Hippocrates of Chios. He is called Hippocrates of Chios. You can always go and check, born 470 and died around 410. Thank you very much. Thank you. Thank you.
Thank you very much, Arnold. If you can just stop your sharing, please. Thank you very much. Colleagues, we're moving to the final session for today that will be presented by Peter. Some demonstration of concepts in science and what goes with that, also with GeoGebra. You would have noticed that the problem that Arnold presented on GeoGebra was not exactly the same as the one that you had on your phone. It was a slightly different version, but exactly the same strategy and so on. So please play around with the applet and see to what extent you can also then just replicate what he has done at your own time. We will share all of these links, the hyperlinks, as well as the QR codes with you afterwards. So don't be worried about access afterwards. This is something that you can revisit at any time. But for now, Mr. Peter Weisvanger, he's responsible for our science development components and program as program leader. And I think he will just share some very exciting GeoGebra Applets for also teaching physical science or to demonstrate scientific concepts or results, or to just use it for the promotion of STEAM education in the context of physical sciences. Over to you, Peter.
All right, thank you, Werner.
Just let me just share the program, colleagues. Sorry about that. Unfortunately, the person who was supposed to present the second session on the 21st century pedagogies, very exciting. We'll try to get her again with our next webinar. She couldn't make it due to load shedding and some battery issues on her side. So this will be the final talk then, and hopefully we will finish more or less in time according to the program as indicated. So over to you, Peter.
I don't want to go into any major detail in any of the scientific concepts, rather to show you how GeoGebra can be used to illustrate concepts and the various factors that influence those concepts and the interrelationship between concepts. Because without understanding all of that, the learner cannot understand so many of the problems. And this is where GeoGebra actually is a very powerful little system, if you want to call it that. Okay, let me bring up the first one here. Okay, fine. So we have our little arc of the water, actually describing what the water does, and its interrelationship with air friction and everything else is beyond maths and beyond science because of the intricacies involved. But we just want to get a general idea of what the shape of this is. So we're going to choose 3 variables, one for the curvature, one for height, and one for width. So we do that. We choose our variables here. Let me just move this. And then we need a graph. Okay. Here we have a flat line because the variables are 0, 0, and 1. And now we have to adapt the variables in order to model this water arc. And let's try and bring it a little bit this way and then move it up and almost. Okay, now the one thing, it doesn't stop in the right place, it doesn't start in the right place, so you set some limits. Let's say the left limit here would be something like minus 7.4. Okay, enter that. Okay, more or less. And the right limit would be about 8.4. Okay, more or less. Could be slightly longer. But here you have then, in terms of this function, a description of this arch, of this curve. It models what nature does, or it gives a description of nature. This is using mathematics. If we want to do the same thing in physical science, we do the following. Okay, and you should be able to see this. I'm still sharing. Vanna, can you see a new one?
No problem.
Okay, good. In physical science, we start with different variables. We still use 3, but we're going to use the height here above. We use angle, we use height, and then initial velocity to see whether we can model this curve there. And there's a try again button because doing it first time round takes quite a bit of effort. But you know, this is how the learners will come to understand vertical projectile motion or projectile motion, what it is about. So we just move up there, perhaps not quite as high. Then we want to set the angle quite nicely here to about 55, and then the initial velocity. So let's set the velocity to about 10. And then we fire our cannon and see what happens there. So we click our start. We've missed the target a little bit too far. But, you know, you can always try again. And that's the beauty of computer simulation. You don't have to set up the experiment from scratch. You can just run the simulation a second time. So let's reduce the initial velocity by 1 meter per second and then start off again. So we'll start, oops, that is too low. So we need to go a little bit higher. We increase, let's 9.5, and we try that. And, well, as good as perfect. We're not going to get it that much more accurate, but immediately then with GeoGebra you can do all the calculations that are related to something like that. The maximum height that the water reaches and at what time. So by allowing a learner to play around with this on their cell phone, they very quickly begin to understand the relationship between those three variables. And hopefully when they have to reproduce that kind of work, then in an exam, it will go so much easier. The one thing about is I have these buttons for up and down because it is easier than putting your finger on a small little point and moving that up or down. But that's enough of that. We don't want to stay here too long. Okay. There's so much that is done in GeoGebra that you can use in the classroom to demonstrate. You know, for example, this particular one, the ripple tank. You have a class of 40, 30 if you're lucky, and you gather them around a small little ripple tank with a vague light underneath, and you must see the grey little movements along on the white paper. Why not show them this ripple tank demo as a computer simulation? So we start. Here's the up and down sources creating the pulse and then the wave moving out. And you can very quickly change the distance in between. You can increase the amplitude that these two white little balls produce, and you can change their frequency. The whole idea is we want to see where's constructive interference, so you click, there's your line of constructive interference, and you can clearly see the waves there that are peaking at that particular point. Or the destructive interference, the red lines where there is virtually no movement. And to illustrate that further, we have these two, the yellow and the purple ball there, and we turn the demo to the side. And you notice that the yellow ball with constructive interference is bouncing up and down quite merrily, whereas the purple ball is stationary. That again, what is constructive interference versus destructive, illustrated very simply with a 3D ripple tank demo. So, you know, you can always do the ripple tank after this, so that the learner has got a grasp of what they are supposed to be looking for, and then find that in the actual app. Yeah. Okay. This is my gripe about grade 10 physical sciences, where we do superposition. We are told very simply, this is, you know, you just add the two amplitudes and that gives you your superposition. But that's not what superposition is at all. Let me just demonstrate. Here we have two pulses, and they are now going to superimpose, move over and through each other. And you can see now what actual superposition is and why you do an algebraic sum. Then you can change the widths of these as you want to. Let's just I must come up here. The width we must increase. Want to increase the width to 5, and we want to bring this one further down. Okay, there we are. And these are two identical. There should be pause. Okay, now we go step for step a little bit further. And they now are, well, they have superimposed. We must bring them across. There we go. Okay. Oops, too far. Perfect superposition, perfect destructive interference, where there is no pulse visible for that brief moment in time. You know, the big thing about superposition is that these pulses move through each other and that's the important part, then continue on their journey as if nothing happened. And we continue with that. We have these two squares. They then move on through each other. So again, another application of GeoGebra in demonstrating these science concepts and being able to change from a mixed form. You know, this I would call this a dance, not just superposition, because I mean, look at that motion there. Okay, but yeah, it's getting late in the day. We don't want to go into too much motion. This little applet is the AC generator. You can run it clockwise or anti-clockwise. You can show the magnetic field lines, and then you can run it. This in the 3D, so let's run. Okay. Now, note there's on the little graph, this is clearly AC current from a positive to a negative. Note the little arrows here in the applet, how they change, and that they change particularly, at a particular time when it runs through there. You can see you have a split ring commutator that transmits the current as it is, changing back and forth as the coil turns in the magnetic field. So a nice little illustration of a AC generator that the learner can play with and then compare. Okay, what is happening there? Okay, here the little dot is, we're moving across the 0 line when this should be vertical. So they can test, they can experiment on their phones with an applet like this to understand clearly what is happening. If we want to put in the force vectors, there you can have your Fleming's right hand rule to determine, is the direction correctly indicated, the force and the direction of the magnetic field. Okay. Yeah. I want to actually just do, we have 5 minutes left, so let me do these two things. Okay. The biggest problem very often in mechanics is that learners don't know how to link position, velocity, and acceleration. So why not give them a little game where they can then very quickly get to grips with this. And you as a teacher have the option. You set your acceleration, various values there, anything that you would like. Then you ask the learner now with these pink buttons to actually sketch the velocity versus time graph or the position versus time graph, and see how well they can translate acceleration into constant velocity or changing velocity, and how that relates to position. So we start with a positive acceleration. So let's start here at 0, the velocity, and there's an acceleration, so we're going to move faster. Now we come down to this level, which is 0 velocity, which means the velocity is remaining constant. Now there's negative acceleration, so the velocity decreases again, and as much as this increase, that decreases. So that's the increase, the decrease. And now we have a even larger increase in the acceleration, and we move this, shall we say, up there. And now to check this graph. And you can see, okay, velocity ultimately also depends on the initial velocity, so we can bring this down, and you can see immediately that what the learner, being me in this case, kind of illustrated the velocity versus time graph should be, fits perfectly with the acceleration we have just now. You can do the same with position versus time. I'm just going to illustrate that. This is the position versus time graph for this acceleration versus time graph. So you can play around with this an awful lot. Let me just reset and just do one other one and bring this down, and now like this. Okay, think for yourself now just quickly, how does the velocity increase and what's its shape? Velocity or acceleration here and here is constant, so those graphs must have the same gradient. So let's bring that up there and that up there, and this is the same, so let's bring that up there, and we bring this here and there. Okay, so am I right? Yes. Here you have a negative acceleration, and it is constant for both. That means this line must be a straight line. There can be no kink in it. It must be straight to indicate that it is a constant acceleration, and the slope, where am I here? Oops, there. Sorry, made a mistake here. So this line and that line is also the same gradient, meaning the same velocity. I can check this here with a much lower initial velocity, and at the 0 initial velocity that we chose, we mirrored that perfectly. Now, the position versus time graph is going to look something like this. Like the old army helmets, the Stahldacker that they wore, the young guys going into the army, something like this. We'll model it, there we have it. Okay, where you have a positive acceleration, then negative acceleration, and positive acceleration once again. So by moving this, we can, this is not quite, let's leave that. Okay, let's just take 5 minutes. I want you to try this on your cell phones. So I'm going to just stop sharing this here for a moment, and I'm going to do, I should have just my applet there, and try and open this little QR code with your phone. It'll take you to a applet on refraction, just so that you can actually play around a little bit with it on your cell phone if you have. So it's your QR code, just scan that. Won't take you long, should be a minute at most. And then I will now go to a new share where we go into our GeoGebra. Where is this? Okay. And let us just escape. And here we are. And here's the actual applet for refraction. The incident light, so incoming ray, then you always have some reflected light, but some of the light passes into a new medium and is then refracted. Here, if we drew a straight line through it, it would tell you to what extent that diffraction takes place, and this is the actual angle of refraction, and that's indicated in these values there. And everything underlined here is Snell's law. So once we know what Snell's law is, we should be able to apply this and play around with it. Here you have refractive index of the medium above the line, then the refractive index of this medium below. 1.3 is for ice. Let's increase this for a sugar solution. And as you can see, the refraction has been far greater. And if I now change the angle of incidence, you'll notice that the angle of refraction also changes as a result. But proportionally, the change in the angle of incidence will always be greater than the change in the angle of reflection. Okay? We're not worried about the refracted light, or the reflected light. That'll always be there, and then here the refracted. Then you can ask the learner, now demonstrate critical angles or total internal reflection. And clearly, if the learner has been listening to your presentation, you will know immediately that your refractive index here must be higher than for the medium it's going into. Okay, so we have a higher refractive index in this first medium, lower in the second medium. You can see that already, where the line of the refractive ray is now bending in the opposite direction. And if we play around very carefully with this, just moving it little by little, oops, that's just a bit too much. Let's bring this back. We now, so we can gauge the exact angle of the critical angle rather. So let's go up here slowly, and there we go. Okay, here critical angle is 61,23 degrees, and there we have it. So we can always calculate this using Snell's law, or we can demonstrate it here. So again, the learner, by playing around with it, can get to grips with this concept that they have to apply in different ways. And this is a task for you when you want to. We have again refraction as it strikes a particular surface. But now we don't have a simple block, we have an L block. And the challenge is to change the point at which the light enters the block, to change the refractive indexes of the two materials and the angle of incidence, and see whether you can cause total internal reflection on all these surfaces except the one at the top, because you can't get the ray there. But you should be able to produce that here, should produce it along that line, there and there. Just to demonstrate that already a little bit, there you see, okay? Just with this particular configuration, here we have total internal reflection of this line here. Okay, now it is up to you to actually play around with it. We will send you the QR codes for us, or the actual URL, so that you can open this in your laptop and play around with it, see how good your understanding of just the very simple concept of refraction is, to then take this a step further. So thank you very much for listening to me in this rush here. You've got a poll going, and we would like you to answer those. Thank you very much.
Thank you very much, Peter. Colleagues, it's getting late, so I really appreciate your time, and it's done slightly later than what we wanted to. There's a little poll going that Karin has put together, or I don't know, maybe some of my other colleagues, so thanks a lot for that. Please respond to that as soon as possible. All you have to do is just to respond on your Zoom screen actively. But from my side, I would like to take this opportunity to thank all the presenters and everybody that participated in this pilot project. I must emphasize this is a pilot project where we try to just show in a small way the power of GeoGebra as a free open source program that can be utilized with very low data and very cheaply to interact over distance or otherwise with our learners. And I think it has great potential for experiential learning through Applets, anywhere, anytime. And hopefully we can also, from your side, get some advice, some comments, how we can improve. We plan to have the second webinar in a series of 4 this year in May. And we'll use this opportunity and feedback we get from you also to try to improve the experience and to try to make it as enjoyable, as valuable in terms of learning. Please, remember that we will share all these materials also with you via the email. And we will keep communicating to set up a community of practice for those who want to become more involved, and even for those who would like in future to be part of the team who present some of these applets for mathematical problem solving or for science demonstration, or even just to promote STEAM education in the country. I don't know if there's anybody who would like to make a comment at this stage, but with that, I would like to bring this webinar session to an end. And once again, I thank you for all your time and patience. And it will be great to participate with your phones using the applets. And in future, we try to improve the opportunity for you to do so, to have maximum impact and value from these sessions. We wish our educators all the best and look forward to interact with you again during our second GeoGebra Innovative Practice for 4IR webinar in May. Goodbye.